Chapter Statistical Inference 1, which is chapter 17 of Gupta Kapoor. Here the first topic is here the first question which arises is what is an estimation? What is an estimator? So let us consider a population of x1, x2, x1, x2, x3 till xn. So if we consider a population, then we take any estimator. For example, in this whole chapter, we have taken a generalized estimation, that is t. So T is an estimator which estimates certain parameters. Now, what are parameters? Parameters are like mu and sigma square, which tell us or gives information about the population, and those we call it as population parameters. So the first thing which we consider is, okay, what are the, okay, you are telling that estimator. Now give an estimator. Now, for example, me myself estimate my marks to be like out of 100, I expect my marks to be 95, and so I here function myself as an estimator of my marks being the parameter. Okay, marks being the parameter, to be precise. So for example, if I get 90, so I am an estimator, that is I am T, and that theta is marks, that is 90. So now, okay, so now so now what are the characteristics of estimators? Like, what should be the characteristics of me to be a very good estimator? So first thing is unbiasedness, that I should not be unbiased to my marks, that I am only preparing so I should get more marks. No, I should be unbiased. I should be unbiased, like I am estimating with my preparation and stuff. The next thing we come is consistency, that how consistent I am, how consistently I am estimating the how consistently I am estimating my marks very nicely and very precisely. The next thing is my efficiency. Efficiency is like with efficiency comes under the circumstances that with how much minimum variance and consistency. Like here it is like I am expecting my marks to come to be 95, and I actually get my marks to be 90. So there is a variance of 5 marks. For example, uh, if you estimate my marks to be 93, and I get 90, that means you are a better estimator. That means you have a better efficiency in estimation of a particular parameter than me. Then comes sufficiency. Sufficiency comes under the circumstances that the sufficiency is generally we check, and the major complexities come under the topic of sufficiency. Sufficiency is we check that whatever we have, either it's sufficient, or also we check that if a parameter is unbiased, consistent, and efficient, then is it sufficient for an estimator's point of view for that particular parameter. So it becomes a bit complex. So let's start with the first thing, which is unbiased. Now the basic form of unbiasedness is that an estimator is said to be unbiased if expectation of Tn is equal to gamma theta. I should be unbiased if the expectation of estimator, that whatever be my expectation, it should be exactly equal to the parameter. What is the parameter? That is being my marks. That is the expected value given by Tn should be equal to gamma theta, which is written as expected value of Tn is equal to gamma theta. This is an expectation of an expectation of an estimator, and gamma theta is the function of a parameter. I hope you understand till this much. And if now coming into the questions part, if I take example 17.1, then here we are given the value of t as 1 by n summation xi square I running from 1 to n, and we are here this is the t, which is the estimator has been given, and the parameter to be to calculate means जिसका हमको वैल्यू एस्टिमेट करना है, that is mu square plus 1 or 1 plus mu square, whatever you can take. Now here I think it has now here the question says a random variable from a normal population mu 1. So when we are given with normal population, simple, that expected value of xi is given to be 1, and variance of xi is given to be 1. Sorry, this is mu and this 1. This is given. Okay. Now now we want to calculate the expected value of xi square. Okay, so for xi square we use the formula of variance, that is variance xi is equal to expected value of x square प्लस एक्सपेक्टेड वैल्यू ऑफ x का होल स्क्वायर। ओके, हमको निकालना ये है और हमको ये दोनों का वैल्यू दिया हुआ है, दैट इज 1 इक्वल टू एक्सपेक्टेड वैल्यू ऑफ म्यू स्क्वायर, दिस इज माइनस sorry x square minus mu. Now taking this, expected value of x square becomes mu square plus 1. Okay, we have now let's mark this equation 1. Now generalized or the standard formula of unbiasedness is that the expected value of t should be equal to the parameter which you are considering, that is mu square plus 1. Okay, so now we are considering the expected value of t, that is given by expected value of 1 by n summation of xi square I running from 1 to n. Okay, now since 1 to n is a constant, 1 to n comes out, and also this summation also we are taking out, so summation of I is equal to n from n expected value of xi square, we are giving this form. Now 1 by n stays as same, summation also stays as same. Now this is equal to xi square, we have already found from equation, that is mu square plus 1. So that is summation of mu square plus 1. Now if we add n times mu square plus 1, like mu square plus 1 plus mu square plus 1 n times, so that becomes 1 by n into n mu square plus 1, which is equal to mu square plus 1. We know for an unbiased estimator to be for an estimator to be unbiased, expected value of t should be equal to the parameter, and it is equal to the parameter. So hence this is an unbiased estimator. We have proved. Now we are done with unbiasedness. Now let's come to the next part, that is an estimator should be consistent. An estimator should be consistent part is very easy and it is majorly theoretical. We do not come across too many questions regarding this. Now consistency. If you go through the definition, what comes out is that it tells about the probability, but for easy understanding, consider that you are taking the estimator Tn. The difference between the estimator and the parameter, that is Tn minus gamma theta, if you take the difference under mod, this should be very small. Very small मतलब कितना छोटा? It should be less than epsilon. Now epsilon is a very small value we consider, like 0.00001. This, now the probability of getting this, that the probability that the difference between the estimator and the parameter should be so less that the probability of this should tends to 1 as our sample space, or n, tends to infinity. This is all what consistency talks about. That's it. Now once we are done with, that's the basis of consistency. You will find you will find theorems, and you will find an example which is very easy to solve, since Cauchy distribution is a very controversial topic and we do not generally have that, so that's why I won't be covering that part. And apart from that, if we move into the next part, that is efficiency, or that is efficiency. Now efficiency is generally calculated between two estimators. For example, consider you to be one estimator and myself to be one estimator. Okay, so this is like me and this is you. Okay, so I am an estimator of myself, my marks, and you are also an estimator of my marks. Now efficiency is defined between two estimators, I have said you. For example, I have a variance of v1 and you have a variance of v2. Now my actual marks is, for example, I have got is 93. You have estimated my marks to be 90, and I estimated 95, and my actual marks is 93. Now I have a variance of 2 and you have a variance of 3. That means I am less varying, means मेरा मार्क्स और मेरे एक्चुअल मार्क्स में जो मैंने एस्टिमेट किया था उसमें डिफरेंस कम है, मतलब मेरा वेरिएंस कम है. तो मेरा जो वेरिएंस है, मैं जो हूँ एज एन एस्टिमेटर, आई बिकेम द मिनिमम वेरिएंस एस्टिमेटर. or the most efficient estimator, most efficient estimator, since why my efficiency is more, because my variance is less. Okay, that's the first thing you need to understand. Now, how do we calculate efficiency? We do not calculate the efficiency of the most efficient estimator. We generally calculate the other one. For example, we want to calculate the efficiency of T2, that is efficiency of T2, then we take V1 divided by V2. That means अगर हम T2 का एस्टिमेट निकालना चाहते हैं तो हम V2 का जो वैल्यू है उसको हम लोग डिनोमिनेटर में रखेंगे, और V1 के वैल्यू को हम लोग मतलब जिसका भी हम लोग निकालेंगे वो डिनोमिनेटर में रहेगा, उसका वेरिएंस. Okay, now this is what estimator is. Now let's move into the next. Now let's solve a question, that is 17.7. In 17.7 we 17.7 we are given with two t's, that is x1 plus x2 plus I'm not writing too much plus x5 divided by 5. This is like the first estimator. Then t2 is given as x1 plus x2 x1 plus x2 by 2 plus of x3, and t3 is given by 2x1 plus x2 plus lambda x3 divided by 3. Now here we have been asked as normal population, okay, unknown mean mu, that is expected value of xi is given to be mu, and since variance is not given, we consider variance of xi to be sigma square. We consider it, मतलब we take it, मतलब say कर दो उसको ऐसे टाइप, ठीक है. Then first we need to find okay, lambda 3 we have to find lambda, that's a different story altogether, but first we need to find whether t1 and t2 is an uh, unbiased estimator of mu or not. Okay, so let's consider the expected value of t1 as we do it in unbiasedness, that is x1 plus x2 plus x3. Since x1 and x2 and x3 is like मतलब 5 बार हो रहा है, so let's consider 1 by मतलब 1 by 5 we take it अलग से, and then summation I running from 1 to 5, expected value of capital xi. capital xi 5 बार जा रहा है तो वही हो जाएगा तुम्हारा 1 by 5 इंटू 5 टाइम्स म्यू. वो तो मीन के वो तो म्यू ही आएगा, एक्सपेक्टेड वैल्यू ऑफ एक्स अगर म्यू है तो ये भी म्यू ही आएगा, तो ये हो गया म्यू. सो t1 इज एन अनबाइज्ड एस्टिमेटर ऑफ म्यू. नाउ वी कम टू t2. सो एक्सपेक्टेड वैल्यू ऑफ t2 जो है वो है x1 प्लस x2, तो ये हो जाएगा. तुम इसको हम लोग क्योंकि एक्सपेक्टेड वैल्यू ऑफ एक्स आई रनिंग फ्रॉम 1 to 2 अगर हम लोग करें तो वही म्यू ही आएगा. सो म्यू डिवाइडेड बाय 2 प्लस एक्सपेक्टेड वैल्यू ऑफ x3 इज ऑल्सो म्यू, सो दैट बिकम्स, तो ये तो म्यू प्लस म्यू बाय 2 आएगा, तो दिस इज नॉट इक्वल टू म्यू, so this is not an unbiased estimator. So T1 is an unbiased estimator. This is a biased estimator. अभी एक्सपेक्टेशन ऑफ E3 में प्रॉब्लम, एक्सपेक्टेशन ऑफ E3 हमको दे दिया है कि वो अनबायस्ड एस्टिमेटर है, तो I'll do it over here. Expectation of T3 is equal to mu. It is given. Now we have to find lambda over here. So 2x1 plus x2 plus lambda x3 is equal to mu whole divided by 3. Now if we take if we take x1, x2 and x3 to be mu, because mu, since t3 is an unbiased estimator of mu, so these value also become mu. So 2 times mu plus lambda mu becomes 3 mu. Here 3 mu, here 3 mu, that becomes 0. So lambda also becomes 0. Okay, now we need to check that which is the most efficient estimator, if I'm not wrong. Yeah, which estimator is best among T1, T2 and T3. For that we need to calculate the variance of T1, T2 and T3. So let us consider the variance of T1, which is equal to sigma square plus sigma square plus sigma sigma square plus sigma square plus sigma square we need to find, divided by 1 by 25. So 1 by 25 times of 5 sigma square, that becomes sigma square by 5. Now if we take variance of T2, that becomes like sigma square plus sigma square by 2 divide that becomes sigma square sigma square plus sigma square divided by 4, that becomes sigma square by 2 plus sigma square, that becomes 3 by 2 sigma square. Yeah, 3 by 2 sigma square. And variance of T3, that becomes 2 sigma square plus sigma square plus 0. So that becomes like 3 sigma square divided by 9, that is sigma square, uh, since it's a constant, so 4 sigma square plus sigma square, that is 5 sigma square divided by 9, so that becomes 5 by 9 sigma square. So ये तो हो जाएगा 0.2 sigma square, ये हो जाएगा 0.5 into 3, 1.5 sigma square, and this becomes 0.3 into 5, that becomes 1.5. 1.5 divided by 0.3, that becomes 0.05. So most probably T3, oh no, हाँ, sorry, ये तो मतलब 1/9 है, तो 0.3 into 0.3 into 5, that becomes 0.15. 0.15 divided by 3, that becomes 0.5 approx. I'm just doing approx. So this is the best estimator, that is the most efficient estimator. Okay, so we are done with efficiency. Then you have two theorems of minimum variance unbiased estimator. Okay, now we will move on to one of the most difficult topics. Now we actually move into the main chapter, that is factorization theorem of name.